arrangement that David gave his, in all sense, inspiring lecture just before mine. This will allow me to go fast through some pieces, but hopefully not too fast. But basically, I plan today, so let me just maybe in a few words remind you the content, or better to say, just the scope of our last two lectures. We learned a method which allowed us to calculate efficiently, and also not only to calculate but to analyze some relevant asymptotic behavior of products of several inverse spectral determinants. Today I'd like to prepare a ground and actually to calculate something for a very similar object which involves just products of spectral determinants themselves. And this is done in the most economic way. In principle, this problem is much simpler, looks simpler than calculating expectation value of product of inverse determinants, because just determinant they are polynomials in their entries, and if entries are random and say independent, then there are various ways of performing these averages. But if you consider product of many of these determinants, then even with one is manageable, but if you need a regular tool to calculate product of many and also to apply it in more complicated circumstance, then it's good to have a tool which you can rely upon and which does a good part of your combinatorial work for you. And this is achieved by using anti-commuting or Grassmann variables, which in some slightly different disguise we already were exposed to. So let me just go through a few definitions, and these are simple objects. So let us call psi1 to psi n generators which will generate corresponding algebra. They just satisfy pairwise anti-commutation relations. They anti-commute, and psi I times psi j is minus psi j psi I. We have our pointer here. Unavoidably, if you put just I equal j, you see that square is equal to 0, which is a nice property which shows us that any function, if you say one variable, if you expand it in Taylor series, will terminate after first two terms. The set of linear combinations of these psi i's with coefficients which we assume to be usual commuting numbers, such a combination is called Grassmann number. And the algebra generated by these psi i's called Grassmann algebra. Okay, I use notation which I don't know, probably found in the literature, lambda to n. I think you use some different notation, but I don't think it's important. So any arbitrary element in this algebra can be written down in this form. Just basically adding up various all possible combinations of these Grassmann generators, and it's immediate to understand that product of an even number of this anti-commuting object is by itself is commuting object, and in contrast to the product of odd number of these generators, which is anti-commuting object by itself. And basically this allows us to say that just to denote lambda plus and lambda minus subsets of this algebra, which are generated by which cover all even and odd powers in psi k. And this decomposition is standard name for it, Z2 grading, and it's easy to see that dimension of each of these spaces is 2 to n minus 1, and dimension of lambda n is just 2 to n. How to see it immediately? Just because all indices in these sums, in this representation, all indices in every sum should be different. The number of different terms in each of these sums is just given by number of possibilities of choosing the given number of distinct indices from n. So sum of these over odd n's and over odd numbers and over even numbers are just equal to 2n minus 1. Now, as I mentioned, a nice property that every expansion terminates after for function of one of these variable terminates after first two terms. So, for example, exponential of Grassmann or anti-commuting number is just 1 plus psi, and that's it. And of course, if we consider similar expansions for functions of several variables, they always terminate after finite number of terms. Now, we'd like also to define operations of differentiation and later on integration involving these anti-commuting variables. And differentiation is defined as follows. We assume that differential operators d over d psi act from the left, and they act according to the following rules. By the way, I noticed that in the handout that I mean in the lecture note that some of you have, here there is a misprint. It's written delta ij, so I corrected here. It should be delta ik by obvious reason. So d over d psi acting psi I acting on psi j produces 0 if I and j are different indices, and produce 1 in case it's I equal to j, and it acts on a product of two according to the following rule. Basically, it means that this derivative acts on the first, and this gives this term, and then you should commute this to the left, and it requires minus sign, and then you just it acts on it. So this is the rule.
As with the previous lecture, that's just the inner product, which is denoted by I. So of course you have to make a proper choice of the vector field x.
Right.
But doing that, this is just the I sub x of David Bridges' thought.
Yes, correct. But even if we, I mean, this is nice to have this interpretation, but I, for deductive purposes, wanted to insist on simplicity of these operations, and they're just very simple set of rules. Of course, this interpretation is valid, but it's just very easy to remember directly. Now, this is in fact surprising, a nice fact, that integration with respect to Grassmann variables is the same as differentiation. This suggestion goes back, I think, to Berezin, who introduced the notion of integral over anti-commuting numbers. And this is basically the rule, how you perform this integration. And this or it's equivalent to the so-called Berezin rules, that integral of d psi is equal to 0, and integral of psi d psi is equal to 1. And this is the only rules we need to integrate arbitrary function of Grassmann variables. Now, if we have several variables and like to perform multiple integrals, then we need to know how psi's and d psi's, whether they commute or anti-commute. The rule is that d psi's are also Grassmann variables. They anti-commute with all psi's and with among themselves. So they just anti-commute according to standard rule. And let me give you an example, the simplest possible example of evaluating integral over two Grassmann variables of exponential minus a psi 1 psi 2. So I just expand in Taylor series. It terminates after first term, and we use these rules of integration. You see, integrating 1 will give you 0 by this rule. So you remain with performing this integral, and you should then commute this d psi to psi, and in order to get possibility to apply this integration rule, this kills minus, and you see that the result is A. Now, in fact, David also did a good service for me, because he proved an identity, slightly different notation, but he proved an identity which I'm going to show you now, so I won't spend much time on it. Basically, this is the following useful identity. It was precisely, I think, that he proved. That if you take matrix A of commuting entries and just usual numbers, and consider the following product, you consider such a linear combination. You sum over second index L, multiply with psi L, and then consider product of all k. Then, as practically what David have shown to us, that you will get determinant of A multiplied with just product of all maximal possible monomial in this order, psi 1 to psi n. Now, for just to introduce some notations which are useful, I will introduce also an operation which is, one can look at it as, in some sense, analog of complex conjugation, but in another sense it's not. It's just an operation which I call conjugation. And I introduce it by two identities. That if you take, so to every Grassmann variable, I put in correspondence another Grassmann variable psi bar, conjugate of it. And if I conjugate it second time, I will get minus psi back. Psi back, but with minus sign. This is unusual. And also, I need to know how to find the conjugate of product of two psi's. And I will require that it's just product of conjugates of psi. So in this way, for any set of Grassmann variables, n Grassmann variables, we have a conjugate set, better say, set of conjugate anti-commuting generators. So you can look at them just as independent set of anti-commuting variables. That's all. But these notations are convenient because they allow us to write kind of scalar product in this sense. Just introduce here. In fact, it's not product; it's square. It's analog of so it's psi bar times it's psi. It's just sum from 1 to n of all psi I bar times psi I. So I think of psi as a column vector with components psi I and components psi I, and in this sense it's kind of scalar product. And in this definition, my scalar product is, so to say, real. It means that its conjugate equal to itself.
Can I
for
a second put this in perspective? It is true that Berezin, in his important book, Introduction to Superanalysis, introduces this involution, calls it an involution, along with a second involution. Calls this of the second kind, and then there's an involution of the first kind, which is closer to what mathematicians and also physicists are used to, where under the bar you interchange the order of the product, and you don't put a minus sign when you do double bar. So there's several involutions. This particular involution was used by Fyodorov in his very important work showing how to use super mathematics to get non-trivial results for disordered systems. I claim that a more modern view, so as you know, personally, I have abolished the bar. So I
Yes.
must make the standard remark. There should be no bar on a Grassmann variable. It's,
Okay, it's just independent set of Grassmann variables. What
yeah,
you can look at it.
rules what is double bar. I mean, you should. Yeah, you can put the bar just like a hat or a prime or a tilde.
Okay, whatever you
or
wish.
Something, or
Yes.
any little thing that distinguishes the psi from another psi. But in no way, if you ask me, should you start doing double bars and things like this.
It's the only. This is the only
It just-
only place where it appears.
It just happens to be an obstacle. In the cases of Fyodorov, it all worked out quite neatly. But if you go beyond that and do other symmetry classes,
Okay.
as you know, you have you run into problems.
Yes.
We let you go because
Thank you, Mark.
we let you go.
Otherwise, I would just step down.
I have to make this remark that you should never. This is sort of my.
But okay, I don't. Okay.
Birnbauer's law to never complex conjugate the Grassmann variable.
It's not complex. It's involution, as you mentioned. And if you look at it, it's innocent in this sense. I think you slightly. I understand your point. I even see which difficulties it may arise on some advanced level. But I think really it's not that important that you just stress it.
And there's
What you do
no
instead?
value whatsoever in saying that something is real here. So
No, okay,
I would scratch
okay,
out that language.
okay.
Okay.
So you would just say that they are independent. So
Yeah.
Yes, it's just a set of independence, but still, especially if you read, as you know, a lot of physical literature, it's used, so at least it's useful to know that such notations exist. But okay, I don't think that there is a point to
But I
seriously
don't
discuss.
understand then when you need this relation, why can you then simply say that they are independent? So, or did
So
or is
you
it
need what?
this double conjugation?
You know, you need to know, yes, how to how you do it, but and all that. But there will be some. I think that one can do it in this way. There are you can avoid it, but I will do it systematic. I don't think that.
To do it allows you to extend the notion of unitarity, for example,
Yes.
which is a standard concept in ordinary classical analysis. It allows you to extend that to supergroups in a
For example.
rather concise fashion. This is the one merit it has, but that's the only one.
Okay, but still we will use some superunitary metrics and all that. Okay, but this or that way, I do not see any contradiction here. I just a set of definitions, and I think Martin should agree with this. And we will proceed with these notations. And basically, as a consequence, as direct consequence of this relation, we are going to demonstrate. In fact, it also was demonstrated by David, so I won't do a lot of work here. It's just to demonstrate that an integral of exponential minus this psi bar times the scalar product in the defined in this way, but it's practically quadratic form with respect to these Grassmann variables, gives you determinant. And this is a complete analog of almost complete analog, part that determinant comes in positive rather than negative power, but this is precisely why we're using it. Analog of standard Gaussian integral. So, as I mentioned, in fact, David already verified it. So you just do simple algebra using that rule that I mentioned, and you arrive at the result that basically I prefer to see that you first do basically these integrals over psi bars on the set of these psi bars, and then you perform you see that what you get is this monomial, and we then integrate it. And you see that all signs come in correct way, and you get determinant. Now an interesting point comes. Suppose you make just a linear change of variables. You replace this a psi here. It's vector made of anti-commuting entries, and you denote these entries as psi tilde and like to see it as change of variables in your integral. Then, if you inspect this, you replace this by psi tilde, and it's linear relation. And you then, the only way to arrive to result that is gives you determinant of A in the end is to require that this product of differentials, d psi n to d psi 1, is changed, is replaced with product of new differentials, which is multiplied with determinant of the matrix with which we make this linear transformation of variables. And this should be contrasted with usual linear change of variables for commuting for integrals over commuting variables. Of course, if we change variables in the usual way for commuting vectors, we know that here comes 1 over determinant rather than determinant. So
And Jan, you know there's a simple reason for this, and that's that the notation is wrong. D psi should be d by d psi, right? And you wrote it earlier.
Yes. So, what means notation?
What the deep psi?
Yes. Deep psi. Where is it?
Well, you're writing
Yeah.
is to assume that deep psi n and so on.
Yes.
The deep psi should be the partial derivative, d by d psi.
Okay. Yes.
Then everything makes sense.
Yes. Yes.
Because physicists, I mean, this cannot be changed.
Okay. I was afraid that here something is wrong. Here everything is correct.
Life,
Yes.
It's sort of become the convention to do this, so you can't change it anymore. But it leads to the fact that you get to see odd things, and it could look perfectly obvious and natural if it was written in a proper way with a partial derivative.
Yes. Okay. But I mentioned that integration is in fact
Okay, so you
derivatives.
need to remember that, and then this formula makes immediate sense. Doesn't require
Yes.
explanation.
I think that, okay, again, anyway, this is completely obvious that this should be the rule. As Martin mentioned, the reason in different notations you even do not need explanation, but I just think that this is the way it's usually explained. Okay, now we have everything, all necessary tools to perform the job that I promised, to calculate the correlation function of a type which involves product of a few spectral determinants or spectral parameter minus h, where h I've taken from this ensemble of random matrices with Gaussian measure, of Hermitian random matrices with Gaussian measure. And it again depends on this spectral parameter. And I put here f instead of b, and now already educated by David, you know, probably understand why I put b in first case and f in the second case, because we associate these anti-commuting Grassmann variables with, in some sense, with classical limit of fermions. And that's why when we deal exclusively with Grassmann variables, I frequently put, I mean, it's not my connection, everybody does it more or less. Put as a reminder this superscript f and b in case of usual commuting variables, which are in some sense associated with bosons. So let us again start with the simplest possible case n equal 1. We replace every determinant with just Gaussian integral over anti-commuting variables in the sense explained before. And we need to perform the average of this object. But now we can go precisely along the same route in full analogy. What is nice with these notations involving Grassmann variables, that all calculations that you already learned on example of inverse determinants with practically go unchanged if you use the instead vectors with anti-commuting components. Okay, I try, at least I try to present it in fully parallel way to previous calculation. So we associate with, again, if you remember, with each vector we associated one rectangular matrices. In fact, this vector formed such a matrix, n times 1, and also I introduce a vector with this involution or conjugation, which is a row vector with these conjugated variables. And look at it as a matrix of size 1 to n. Then, if we consider product of these heads, again, remind us that we look at them as the matrices and may multiply them as matrices and using usual multiplication rules for matrices. So after trivial algebra, you will just find that this object, which appears here in the exponential, up to minus sign, can be written down as just trace of h times psi as a matrix multiplied with psi with this involution. Why it is useful? Because we can again use the formula that we already used many times. And just let me remind you that if you have, I think it was with I sign that time, I trace of h times k equal to, I write it exponential minus 1 over 2n trace of k squared. And I remember Martin's remark when I first presented it. He said, for which matrices is you mean this? And I averaged over G. I said for matrices with complex entries, and then Martin made a valid remark that later on I'd like to use it for matrices just with whose entries are elements of that yes, commutative part of that algebra. And this is precisely what I'd like to do now. But because they're commutative, all the rules for them are the same practically, and still this formula is valid. Here you see I use it without I here, and so it comes with plus sign here. This is the only difference. Okay, and we immediately see that that what comes here is trace of this matrix, and trivial calculation just explicitly using entries of this matrix shows that it's exponential minus 1/2, and here scalar the scalar square that we defined squared. So the bottom line is that our integral for n equal 1 is given by this is this integral where I just probably forgot to mention. I say it somewhere in my notes that this is just I use this for brevity, for just abbreviation for product of all relevant differentials. Okay, let us leave it here. So what to do now? We know that we can use for similar calculation n equal 1 and later on for arbitrary n, we use two different methods. We to handle it, we use either Hubbard-Stratonovich transformation, or we used a trick which exploited some invariance in of the integrand. So I here will start with Hubbard-Stratonovich transformation, and it just in the same way as before, we write. So let me remind you, for those who still are not very comfortable with that, exponential of minus something squared can be always represented as paying a price of having extra Gaussian integration as exponential of this new integration parameter times linearized version of this. And in this way, we can very easily perform the integral. By the way, we never ever encounter any convergence problem, neither for n equal 1 or for large n, for Grassmann integrals. Therefore, here, in all cases, if we use Hubbard-Stratonovich transformation for in similar circumstances, we can use the simplest possible version of it. We should not care or be concerned with the fact that the resulting Grassmann integral may diverge. If it would be, we remember that we encountered one situation when integral involving usual vectors, a similar integral, was divergent. Here it cannot occur whatsoever. So we have simple Gaussian integral. We know how to perform it. It will be determinant of the corresponding quadratic form. Here it will just give this factor raised to power n. And after simple rescaling, we see this integral representation. Integral over q goes from minus to plus infinity for the expectation value of our characteristic polynomial, or spectral determinant, as I call it, which is the same. And you immediately see that, first of all, it's polynomial in Z, as we expected. It's quite famous polynomial. It's you immediately can see from this representation, or just to derive this so-called, I think it's called Rodriguez formula, showing that this is a famous Hermite polynomial. So so far so good, but let me show you a slightly more fancy procedure, but which proves to be very useful and will be useful in the later stage. In fact, you can do things which are closer to our, in fact, an analog of our second method, or first method, I don't remember in which order they were given, just using some invariance in internal space. And this proceeds by the following observation, that if you have integral like that, just, in fact, it's Gaussian integral, if you wish. It's, of course, Gaussian integral. So we know immediately the left-hand side, but it will be used. We know that the result should be p to n with, yes, p to n, and that's it. However, one can write this p to n in a fancy way. One can write it as an integral from 0 to 2 pi with appropriate coefficient in front of exponential minus n p exponential I phi minus I n phi integrated over phi. How to check it? Very simple. You just expand this term in the exponential in Taylor series and use the fact, use kind of orthogonality property for integration over unit circle over phi. That exponential of I difference of two but to say that any integer times phi, d phi is 2 pi in case this integer is 0 and 0 otherwise. Then you see that the only term which will be picked up from this sum is L equal to n, having this term in mind, and this gives you immediately p to n, and these coefficients just cancel terms which come from expansion basically cancel this prefactor. So you immediately verify that this formula is correct. So why to do it? Because it will help us to rewrite our integral in a slightly different form, which later on will be generalized. So, in our particular case, look how I like to use it. You see, in our particular case, this is integral. Of course, we know that this, and this is our p. So this is our p, and I use this formula. I use this formula. But now I see that I can perform back Gaussian integral very easily over Q because it's standard Gaussian integral. And this is the result. So, which is useful to write down. I mean, integral from over phi from 0 to 2 pi, one can identically rewrite using just integral over the contour, which is circle of radius 1 of in the complex plane of variable psi. So we see, and just some coefficient, appropriate coefficient in front. So we have an alternative representation of our object, and it's also well known. It's basically a representation of Hermite polynomial in terms of contour integral. It's well known, and this is the way we obtained it. In fact, comparing our original formula expressing this expectation value of determinant in terms of our vector integration over these vectors psi and psi bar, we observe a curious correspondence. In fact, we had, you may compare, we had function exponential of z, this scalar product and this scalar product squared. And we have here first two terms just literally the same terms. Now, exponential minus n log is just xi to minus n, and divided by xi it gives you xi to n plus 1. And it turns out, in fact, it looks like a special case, but it's enough to prove a general formula, the following curious correspondence, that integral of a function, any analytic function of this combination of this scalar product is nothing else as up to appropriate constant factor is integral in complex plane over unit circle of f of n times this variable psi, at least I prefer to write it in this way, with such a factor dxi divided by xi to n plus 1, where n is nothing else as dimension of vector psi. It's valid for any analytic function f, and this correspondence and its high dimensional analogues in random matrix theory jargon is called bosonization, although I personally, we all have our own idiosyncrasies. Martin dislikes conjugation. I personally dislike this bosonization. I don't think it's very illuminating, although it has, I mean, there are some reasons to call it. But I use it because it's what seems to be now standard notion in the literature.
Maybe we can discuss briefly why that formula has a chance to hold. On the left-hand side, we see f as a function of the scalar product of these Grassmann values, psi bar and psi. And then we do the Berezin, the integral over the attributing values. And that means we have to do all these differentiations. We have to pick out the top degree, and that's obtained by, one way of thinking about it is that you differentiate many times. Well, how many times? It's n psi's and n psi bars. But since the function only depends on the inner product, basically taking, in a sense, n times the derivative with respect to the argument. But now comes Cauchy, who says that well, Cauchy's theorem tells you that the right-hand side can be worked out by, or the residue theorem, if that's what you know better. The right-hand side says that you can compute this as a residue, and the residue is the nth derivative. Since the psi appears to the power n plus 1, you want to compute the nth derivative of f. So on both sides, you're computing the nth derivative of f. This is why the formula is true once you put in the normalization constant.
Okay, now generalization to n larger than 1 here in this for this object goes without any problem, and even its asymptotic analysis, and I just present notations for this generalization necessary for this generalization. So now, what happens? If we have a product of few spectral determinants or characteristic polynomials in this way, we represent individually each of them as Gaussian integral or Gaussian-like integral over individually this psi and psi bar vector consisting of n anti-commuting variables. And in this way, let us introduce two matrices, just matrix which has these vectors, psi1 to psi n, as column vectors, n of them. N is the number of determinants in our product. And matrix which has conjugate vectors consisting of these conjugated variables as its rows. We can build then product of these with that and immediately see that it will be matrix of commuting entries, and every entry is nothing else as this scalar product which we introduced before. In full analogy with corresponding notation for the case of inverse determinants. And this is one of notational advantages I see when introducing this conjugation, because it looks precisely like in the old case for when we calculated inverse determinants. So it's just fully parallel, looks fully identical, or almost identical. I think it's some advantage, although I am aware of disadvantages that Martin mentioned. But for our goals, I think it's advantage. Now, after the standard manipulations, you perform just do the same, all the same steps, just slightly taking care of signs when you commute psi past psi bar and all that, and you will arrive to the following representation for our object, expectation value of product of n characteristic polynomials, and then again do the same trick. Apply Hubbard-Stratonovich transformation with Hermitian matrices. As I mentioned, we never will have any convergence problem, so we can do it. So you do it, and again from this point you can proceed into different bi-equivalent ways, precisely in the same way as in n=1 case. On one hand, you can just evaluate explicitly this integral, Gaussian integral now, over this set of small case n Grassmann vectors, and get determinants of this quadratic form, z plus I divided by square root of n q, where q is our matrix used for Hubbard-Stratonovich decoupling, raised to power n, and substitute it back to our integral, to this integral, rescale q in standard way, and you arrive to the following convenient representation, which should allow you, obviously, we see that n comes in front in exponential, should allow you standard saddle point analysis. Okay, you can do it in various ways. I suggest to diagonalize Q, it's Hermitian matrix. You diagonalize it with unitary matrices in the same way as we proceed yesterday. Q is a matrix of eigenvalues. The only difference here that here integration goes over all Hermitian matrices. Similar formula in analogous formula for inverse determinants involved, I think, integration over some at least in the point when we use the diagonalization over positive definite Hermitian matrices. But here it just goes over all matrices. You write measure, you already seen it a few times in a standard way using square of van der Monde determinant and Haar measure on UN. And in this way, you can try to evaluate the corresponding integral. Just to make contact with previous case, let me assume the following. Just consider explicitly the following simple case. I assume that n is even and it's even number, so it can be written down as 2 times p. P is integer, and I also assume that all real parts of these spectral parameters, z, let me remind you, because I don't think that I've written it accurately today. Z is a matrix of these spectral parameters which enter individually in each characteristic polynomial. So I assume that real parts of all these is just the same and equal to z naught. Yesterday I assumed that z naught even further, that z naught is 0. Here I just decided to show what happens if it's not 0, but it's not a great deal. So it's just all equal in z naught. And I also assume that half of imaginary parts of these z's, say first p of them, have positive imaginary part, and the rest has negative imaginary part. But please, in this point, in order not to be misled, just I use it for illustration purposes. One can do it without any modification for every matrix S. It's just to show you some analogs with expressions which appeared yesterday. So I consider this particular case. Okay, so S is now diagonal. It has ones and minus ones. First half is ones, and second half is minus ones. And we also assume, in the same way as yesterday, that imaginary part scales with n in such a way that product stays finite when n tends to infinity. And I'd like to perform large n limit and extract corresponding behavior of this correlation function in large n limit. So the structure is very reminiscent of what we had yesterday. Namely, we have integral with large exponential minus large factor n, which should control our saddle point approximation. Here some function whose stationary points we need to find. Van der Monde determinant squared. And then integral, here just a factor depending on q's, of course, which first of all in this limit does not have n in it due to this assumption of scaling. So it's of order of 1 when n tends to infinity. and it has the following structure in it. The saddle point equation is found if I just take derivative of this and set it to 0. Here it's written. And for each individually, for each q alpha, it has two solutions. So altogether, for all small case n variables, we have 2 to n solutions. 2 to n relevant saddle points to be considered. And in similar situation yesterday, it was only one saddle point because our integration domain dictated that we must have them with specific sign, but here all of them are allowed and all should be in principle investigated. So if I look at Q as a matrix, just diagonal matrix with entries Q1 to Qn, I see that saddle points practically are matrices of the following form. This is, by the way, quadratic equation, right? It's quadratic equation, so solving it, for Q, you will see that it's in the following form. It's I times Z naught over 2, then identity matrix, plus, here is just notation, pi times rho of Z naught, where rho of Z naught is given by this expression, and I will show you probably tomorrow that this combination is nothing else as mean spectral density of eigenvalues of GUE matrices if modulus of Z naught smaller than 2, which I assume. And now comes an arbitrary matrix which has pluses or minus in each of its diagonal entry. All of them are saddle points. So this is basically what we have. However, here, in order to understand which of these saddle points in fact dominate our integral when n tends to infinity, you really should take care of the factor which you have here, Vandermonde factor squared. You will see that since you have only plus or minus 1, there will be many constellations. Many of these factors, if you just substitute saddle point values, they just vanish. It's quite clear, and then direct analysis shows this, that what you are after a combination of saddle points which has the least degree of least number of vanishing factors in this combination, because this will give you dominant contribution, obviously. And basically, then you find that the maximal contribution comes from the choice when this matrix sigma is nothing else as your S, which have exactly half pluses and exactly half minuses, and its trivial permutations. In this way, if you find that this is indeed dominating contribution, then you see that you arrive to the following representation of your correlation function of spectral determinants, positive powers of spectral determinants, in a sort of nonlinear sigma model representation, very similar but also somewhat different from what we had yesterday. What is similarity? Similarity is that this integral looks superficially very similar. Integration goes over matrices QS, which are obtained by unitary rotations of matrix S. And but this only is a huge difference. The only difference that here we have unitary rotations, and yesterday we had pseudo-unitary rotations. But on a formal level, this is the only difference. It's important thing that this integral, due to the fact that this is a compact group, or rather integration goes over this coset space, you will never have any divergences for eta going to 0. And yesterday we discussed that you always have this similar integral just regularized by eta, and the result diverges when eta goes to 0 with particular For particular n equal 2 case yesterday, the divergence was 1 over eta, but for higher, for products of more inverse polynomials will be even higher divergences. Here, everything will be convergent, and it's completely clear that averaging product of random variables, which are determinants, cannot produce you any divergences whatsoever. But it's important difference to have in mind. Otherwise, this looks very similar to the previous construction. Now, one also can use trick which leads eventually to this Bosonization. For our particular case, I again use Gaussian integration. There are, of course, much more direct methods, but I like it because pedagogical reasons I think it's very straightforward. Let me remind you, you see, just before, we have here our integral equal to determinant raised to power n. Do you understand how it's? Where was it? Here, in this whole thing. So I'd like to find some useful formula for determinant of any matrix raised to power n, and indeed such formula exists. One can check that for any matrix P with commuting entries, with usual entries, and also probably, definitely, where they are just from even part of Grassmann algebra, but we do not need it. Just there is the following identity up to a constant which one can calculate, but it's just constant depending on small case n and capital N. You just take integral of exponential minus n trace this matrix P times unitary matrix of dimension n from a unitary group, and you integrate over unitary group with Haar measure and insert factor determinant minus nu. This is analog of that. In fact, this is generalization to n larger than 1 of the formula. For n equal 1, it's just precisely that simple one-dimensional or straightforward application of residue calculus, as Martin mentioned. Here is just generalization of these to high n, precisely the same formula. How to verify it? In fact, the useful observation is that easy to understand that the right-hand side is analytic function in looked as function of entries of P. So we can evaluate it, in fact, for convenient choice of P, and then we have it for any P by this property. So let us just consider P unitary, because then it will be really, really easy to calculate. If it's unitary, we use the fact that measure is invariant and introduce P times U, which is product of two unitaries unitary measure. You just introduce this new integration variable, you change variables, and you immediately see that the result is proportional to determinant of P raised to power n with a constant which can be calculated. So in this way you verify this formula, and now you just do the same steps that I've shown to you for n equal 1 case. You have this representation after Haber-Stratonovich. You have this representation for your object. You replace this determinant n using that formula, just substitute it, and perform back Gaussian integral, and you end up with representation of your correlation function or product or expectation value of product of determinants in terms of integral over unitary group. And again, you can perform saddle point analysis for those who, and check that the results will be precisely the same. Just hint for those who will really try to verify it. I recommend you basically go to eigenvalues and eigenvectors of U itself here, and then it will amount basically to saddle point analysis of simple one-dimensional integrals like we had in n equal 1 case. This is effectively reducing problem to n equal 1 for analysis, and you will get the same result. That trick that I showed, in fact, again, as you may immediately understand, it generalizes to an arbitrary analytic function of which depends only on product on this matrix made of scalar products of this n by n matrix that I had, which was made of psi bar of this scalar product. We didn't have name for that, but if f is function only on entries of this matrix, it means arbitrary function of depending only on this product, then the following Bosonization identity follows, for which that formula is just particular case. Okay.
Maybe I can check one remark here.
Mm-hmm.
There's a slight complication in this formula, which is that if you come from the left-hand side and you know f, if you know f as an analytic function everywhere, there's no issue. However, in practice, you're coming from, certainly the way the formula is being used in this context, you're coming from the left-hand side and you've just given some expression in the psi's. And because the psi's are generators of a Grassmann algebra, you're just knowing sort of the polynomial part. In other words, the function f that you want to put on the right-hand side is not uniquely determined. You somehow have to pick some recipe for extending the polynomial that's given to you to some analytic function. You pick any analytic function which, upon restriction, which upon inserting the argument on the left-hand side gives you the integrand that you want to integrate. So there's a lot of freedom, and however, one can prove that this formula is correct for any choice of analytic function that extends the given polynomial.
In fact, one can prove it using only this Gaussian case. In fact, it's yeah, but one can prove it directly without these tricks, of course.
Such an ambiguity did not exist in yesterday's case, because on the left-hand side there was an argument that sort of determined the function that wants to appear on the right-hand side completely.
Mm-hmm. Okay, so now we, in fact, I'm finished with evaluating products of determinant. Yesterday we finished, we understood how to calculate products of inverse determinants. Now it's time to really combine them for good reason. As we have heard many times already, very important information about spectrum of any operator is contained in the resolvent, which is inverse of spectral parameter minus h, and its behavior, in particular its behavior when z approaches a real axis, or support of the spectrum, better to say. And all these tools were in fact preparatory towards the goal of evaluating something related with traces of the resolvent, or in the end of the day, entries or matrix elements of the resolvent. And let me start with the simplest object, which just is mean spectral density, and can be written down. In fact, it's something which I think appeared already in Leonid Pasteur lectures when he used resolution of identity and how to extract it, spectral density from it. So if you take trace of the resolvent, take imaginary part, take limit of the spectral imaginary part of a spectral parameter going to I choose it to positive. So here it's written not plus, which is standard notation in physical literature for approaching 0 from above. So I consider imaginary part, say, positive, and then eventually in the end I'm interested in considering limit to 0 from above and some coefficient in front. Then you recover just mean spectral density. What is mean spectral density? If you integrate it over any part of the or any interval on the real axis, you will get mean number of eigenvalues of our random matrix in this interval. So this is the density of eigenvalues. If you are interested in more, usually mean spectral density is of course the object you start with, and in many applications important, but usually we are not that much interested in it, but we are interested, for example, in studying whether, in random matrix theory especially, whether different eigenvalues are correlated or just independent, look like independent random numbers in large n limit, or some other related questions. And then we'd like to study correlation functions of this of eigenvalue density, and those can be extracted from averaging products of traces of the resolvent and extracting appropriately extracting imaginary parts and all that. I won't go into that. So basically what we should develop effective tools of calculating objects like that, and maybe in principle many more G's involved. And I'm going to show that it's easy to understand that it will amount to our ability to evaluate the following object. It will have several spectral determinants in the numerator. It will have several determinants with possibly and most frequently different spectral parameters in the denominator, and this ratio of the two products should be averaged over ensemble of matrices H. So we now know how to average separately numerator and separately denominator, but the application requires simultaneous averaging of the ratio, and this will be generalization of the method that we already used.
Here I've got a question.
Mm-hmm.
Is there really physical motivation to study arbitrary or to explore all these things for arbitrary small n, or usually?
Okay,
or is
good question. Definitely there are meaningful objects, at least I know, which involve, for example, 4. 2 is standard, it's many things. But it's not because we are not interested in high, because it's the only thing we effectively can analyze to the end. In scattering theory, if you are interested in correlation or cross-section or of correlation of conductances in solid state context, you will easily, we immediately come to necessity to calculate 4. Higher, you can be interested in distributions of, say, conductances, and in principle, in some setting it may require calculating arbitrary moment or maybe generating function. In practice, we rarely go beyond 2, unfortunately, and but challenges are, although they are heavy, but they are purely technical. They are not principal. Everything can be formulated as appropriate nonlinear sigma model integral, but maybe this will be integral, which in the end of the day involves, I don't know, 8 integrations or something like this, which is not that easy to analyze or something like that. Okay, the simplest possible object is just, if we are interested, say, only in this spectral density, we just like to average trace of the resolvent. And my claim is that it's nothing else as derivative of the ratio of two determinants written. Why so? If it's not evident immediately, let us write it in this way. So we have this determinant. We can write it as determinant of practically that's it. So what I did, I just used the fact that determinant of a product of two matrices is product of determinants and use it to cancel factor in the denominator. Now I should perform a differentiation over t. There are various ways of doing it. My favorite way is to write it down as exponential of trace of log trace of log of this operator, or this matrix, 1 plus t z minus h minus 1. And then you need to differentiate and set in the end, which is very important, t to 0. So you may just consider t to be small, expand it to first non-vanishing term, and you see that we will get exponential of t times trace of the resolvent. When you differentiate and set t to 0, you get the object you wish. So this is the way. Or you may find your own way to understand this. The bottom line is that we need to calculate the average of the ratio of two determinants with slightly different spectral parameter and differentiate over this difference and set this difference in the end to 0. So we proceed in the way we already know. We represent the determinant in the denominator, so inverse determinant. We represent as standard Gaussian integral over complex variable or complex vector, and its counterpart in the numerator we represent as integral over anti-commuting Grassmann vectors with anti-commuting entries. And then, obviously, there will be a need to deal simultaneously with presence of anti-commuting and commuting variables. And in fact, we had already example in the previous lecture of dealing simultaneously, in some sense, with anti-commuting and commuting objects, and this was called supersymmetry. So this is why we need to develop a little bit further our tools which will allow us to effectively write and analyze expressions involving simultaneously commuting and anti-commuting variables, which is in the modern jargon is called supercalculus. In principle, I never, probably this is the first time I have possibility to stop precisely after 75 minutes and invite questions, or I can just continue further. It's up to you, in fact.
It's a good place to start, and I'll tell you why. We will have a change of schedule today. Ilya Golchay wants more time to prepare his third lecture. He wants only to teach 2 lectures this week, so we've been thinking how to replace him either today or tomorrow. So we could replace, we will replace him today, and who will step in is Margherita Di Sartori. And in fact, I believe she will just pick up the thread of reasoning from where you're leaving. I'm not going into the big landscape of supercalculus, but just doing the things that are needed to analyze this very object.
Okay.
So I think it's a perfect fit. Okay. Margherita will pick up the argument from where you're leaving it off, and then when she's done in your next lecture, you can go deeper into supercalculus.
Great. It will save me some time.
Perfect sequence of telling the story. Do you agree, Margherita? Yes. So we can have questions now, and questions? I don't think that everything was clear in this lecture to everybody.
So when you use this, instead of the Hubbard-Stratanovich trick, you use this unitary
Yes.
trick. Do you get the same formulas in the end, or do you?
Yes, but after, in general case, it's interesting. If you use it, yes, of course. Of course, answer is I must get it because it's the same object.
So
but it requires some job.
They have different representations.
Yes, there are different representations. It's interesting how you get various relations between the two.
So is one easier to analyze than the other?
Okay, at the moment, okay, it depends on the problem. For this random matrix problem, the simplest problem in hand, I think that it depends on your choice. I personally believe that this thing related to bosonization, I now prefer it in all circumstances. But in the, you see, I'm how it's called, neophyte. Just I learned it not that long ago. I mean, I of course knew basics, but just did calculate. I find it amusing. It nicely works and provides you with insights which usually, and relations which you usually do not notice. So it's, as any effective alternative way to old ways, it's always educating. So I like it very much. But at this level, it's a matter of choice. I think that for more complicated problems, not for all, because really it should be some symmetry, this rotation in internal space, there should be some symmetry to apply this modernization trick. But where it can be applied, I think it should be applied. And things should be analyzed in this way. It's my personal impression, which I got.
Okay, if there are no questions, then let me say it again. At 2 o'clock, we have a lecture by Margherita Di Sartori, and she will, I think it fits very nicely. She will illustrate the methods that have been outlined here at a very concrete, simple example, and take you through the steps. And those who feel uneasy and very unfamiliar, I particularly encourage those to come and pay attention, because I believe that will help them to see how this method works at one example in slow steps. So that's what we will do at 2, and now we have a lunch break.